Okay guys, here's part 2 of the Backpage Pyramid. It's not that I think this will take another 15 minutes, but as I said, I can only record in 15-minute blocks, so I knew I couldn't get finished in the 3 or 4 minutes we had left. Alright, so on the back start to talk about some imaginary solutions. So one thing we need to know, and I think we've discussed this before, but it's worth mentioning, that imaginary solutions, or complex conjugates, we've seen that terminology before, always occur in pairs. Imaginary solutions never occur alone. So, you can never have one imaginary or one complex solution. You can only have 2 or 4 or some multiples of 2. Meaning that if I tell you one imaginary solution, you know that its conjugate also exists. Again, that's terminology that we did before Christmas. So this first function, this g of x function, has a real 0 at 0 and an imaginary 0 at negative 2i. Well, whether I mention it or not, if there is a 0 at negative 2i, there is also a 0 at positive 2i. So in part A, when it says list all the zeros, well, you were already told there was 1 at 0. You were already told there was 1 at negative 2i. And you know that imaginary solutions come in pairs, so there should also be 1 at a positive 2i, because that is the complex conjugate for negative 2i. So this function has 3 solutions. We know that from the degree, and now we have them all. So if I'm going to write this in factored form, this looks like y equals. Now, on the front, I know we talked a lot about finding the Lie coefficient. I already know the Lie coefficient of this polynomial. Just because I don't have an ordered pair and I'm not trying to find it, the Lie coefficient is always the same, whether it's in expanded form or whether it's in factored form. For instance, go back to the one on the previous page. When we found the Lie coefficient to be negative 2, when I wrote it in factored form, it was there, but when I expanded it out, it was still the same Lie coefficient of negative 2. So I know, because I have this polynomial in expanded form already, the Lie coefficient is 3, so I can use that. If there is a 0 at 0, its factor is just x. If there is a 0 at negative 2i, its factor is x plus 2i. And if there is a 0 at positive 2i, its factor is at x minus 2i. And because it said to leave this in factored form, I'm done. And just like I told you on the front, if you wanted to check this, we could put this equation into our calculator. We should see it cross the x-axis at 0 and then no other times because the other 2 solutions are imaginary. Okay, looking at that second one. Again, list all the zeros. Okay, so right away, you should know that there are 3. If there is a 0 at 3 plus 4i, its conjugate tells me there's also a 0 at 3 minus 4i, but that's only 2 solutions. So I'm going to go to my calculator in hopes that I can find that other solution. In the previous one, I told you what it was, but this time I didn't tell you, so my hope is that I can find it from the calculator. So we type in our x to the third minus 4x squared plus 13x plus 50. Go ahead and graph it. I only see it cross the x-axis once, which doesn't surprise me because I already have 2 imaginary solutions. It kind of looks like that's at negative 2. I really hope that to be true. So let's look at the table to verify. Yes, there is a 0 at negative 2. So I have the 2 zeros that we got from the one that was given in its complex conjugate, and the other one is just at negative 2. So again, when I go to write this in factored form, I know what the Lie coefficient is because I already see the general form. The Lie coefficient is 1. My factors would look like x minus 3 plus 4i and another x minus 3 minus 4i. Now I know that looks bad. And then if there's a 0 at negative 2, it looks like x plus 2. So if you're wondering why I used minus, oops, I didn't mean to do that. Okay, if you're wondering why I used minus for both of these, it's because the 3 was positive in both. So because that 3 was positive, I had to use the opposite there. Now, that looks really messy to me, so I am going to clean that up a little bit. Because what's going on here is I'm distributing that negative. So it would look like x minus 3 minus 4i and x minus 3 plus 4i. Okay, so it's not the prettiest thing in factored form, but it's possible. And this is what it looks like in factored form. Because the lead coefficient was 1, if you left it off, that would have been okay as well. Okay, looking at the next one. Write the polynomial of least degree with integral coefficients and zeros, of which are at -4 and -1 minus I, and the y-intercept is at 8. Expanded to general form. Okay, so a lot going on here, and this one's going to take a while because it says expanded general form. But let's start and think about our zeros. If there is one at -4, that's fine. There's also one at -1 minus I. There's a third one at -1 plus I. So you need to get in the habit of, even if I don't tell you both imaginary zeros, they always travel in pairs. As long as I give you one, you can come up with a complex conjugate. So if I go to start this process, this would look like y equals a. The 0 at -4 gives me x plus 4. The 0 at -1 minus I gives me, remember, it's about distributing that negative, so it's going to look like x plus 1 plus I and x plus 1 minus I. Okay, so we knew from this part where it says the y-intercept is at 8, that's an ordered pair of 0, 8. So let's plug that in to find it. So if my y value is 8, I have 0 plus 4, I have 0 plus 1 plus I, and 0 plus 1 minus I. If I clean that up a little bit, 0 plus 4 gives me 4. I have 1 plus I in the second set of parentheses, and then 1 minus I. Now, with those i's, that's not as friendly, but like I've told you so many times, the hard part about quarter 3 is because I'm constantly asking you to refresh your brain with things we've done before. We've done multiplying imaginary numbers. Now, I'm going to choose to multiply those imaginary numbers together first before I deal with that 4. So if I do that, if I'm foiling that, I get 1 minus I plus I minus I squared. Now, the reason why I chose to multiply them together is because if I multiply two complex numbers together, the i's cancel out. These i's in the middle are opposites, they're gone. And remember, I squared is really -1. So 1 minus -1 becomes 1 plus 1. Or, really that part is just 2. Okay? A lot of work so far. Multiply those together, I get 8. So we did all of that work just to find out that the lead coefficient is 1. Okay, now, if this had said factored form, my life would be so much easier, but it doesn't, so I have to keep going from what it tells me. So I can start and say, okay, y equals, my lead coefficient is 1. I have a factor at x plus 4, a factor at x plus 1 plus I, and a factor at x plus 1 minus I. Because it says general form, I have to expand this. If it had said factored form, I'd be done. So I am going to choose to multiply these guys together first. Because again, when I multiply complex things together, the i's cancel each other out. Now I can leave that 1 there, but remember if I left it off, it'd be fine. Okay, so tons to multiply here. I have to distribute that x. So I get x squared plus x minus ix. Then I distribute that 1. gives me another plus x, plus 1, minus I. Then I distribute the I, which gives me a positive ix, plus I, minus I squared. I know that looks messy. I'm not saying it doesn't, but I promise it's going to look better because look what happens. Minus ix plus ix cancels. Plus I minus I cancels. So you're left with x squared. You have 2 x's plus 2x. Now I have a plus 1 and a minus I squared. Remember, I squared is really negative 1. So I have a plus 1 minus a negative 1, which is another plus 1. So this gives me a plus 2. I know that's not pretty, but at least the i's canceled. Now, unfortunately, there's still more to multiply. That 1's not going to change anything, so I just have to distribute the x plus 4. So I get, when I distribute the x, I get x to the third plus 2x squared plus 2x. When I distribute the 4, I get a 4x squared plus 8x plus 8. Then you gotta finally combine all your like terms, which gives you x to the third plus 6x squared plus 10x plus 8. So this is what we look like in general form. Now again, if you want to check this, go to your calculator, go to y equals, plug in what you have. So we have x to the third plus 6x squared plus 10x plus 8. Now all we know about this polynomial is it has a real 0 at negative 4 and 2 imaginaries. So when I graph this, if I did this right, I should see a cross at negative 4 and nothing else. It looks like negative 4. I can verify that on the table. That yes, negative 4 is a 0. It didn't cross any other time. That's because I had 2 imaginary solutions. Okay, let's look at the last one. So given this polynomial, it has a 0 at I. Find all the remaining zeros and write it in factored form. So I should know, or you should know, that this has 4 zeros. If there is 1 at I, there is also 1 at negative I. My hope is that I can go to my calculator and type this in, and the other two would be 2 nice whole numbers, and I'd have it all easy and done, and I'd be good to go. Unfortunately, when I graph this, this does not cross the x-axis at all. That means that all 4 solutions are imaginary. Now, we've done things with looking for the other solutions when I only know 2, and it's all about synthetic division. So I want you to try this with synthetic division, meaning that my first box number would be I, my coefficients would be at 2, no cubic term, so a 0, a 9, no linear, so a 0, and a 7. Try this. Pause the video, try the first one, get an answer, and then try the second one. Okay, so this one was tough. So if you did synthetic division with I, you got to a point here where you had 2i squared, which I put that in parentheses because you had to recognize that was negative 2. Same thing at the end, you got to a point with 7i squared, which was negative 7. So the answer polynomial looked really funny because it had i's in it. But when you did synthetic division again with the negative I, all the i's worked themselves out and you were left with a quadratic. Quadratics are always solvable for us. Now, quadratics can always be solved with square roots or with the quadratic formula. In this case, I'm trying to get this whole box to go away. In this case, because there was no middle term, I could use square roots, but I had to simplify that radical. So when this was all said and done, my 4 answers were I, negative I. Those were from the given information, the given answer and its conjugate. And then we got I radical 14 over 2 and negative I radical 14 over 2. Okay, so what I want you to do is give your homework the best shot you can, and I promise we will go over this some more on Tuesday. Have a great weekend, guys.